Right, so time for our next speaker, Embedded Systems in Space, and it is going to be delivered by Przemysław Szecówka. Przemysław received a PhD in electronics from the Wroclaw University of Technology, where he worked as a scientist and lecturer, researching digital circuits, neural networks and microcontrollers. More recently, as a FPGA designer, Przemysław has a diverse resume under his belt. At Espotel, he contributes to a lot of biomedical and automation projects, while he boasts 5G and super-fast interfaces experience here at Nokia. Also, he has been recently working with Rockwell Automation. He has written a whopping 80 scientific papers, but unfortunately we will only hear and see only one of his talks today. But it's going to be brilliant, and the talk is called Embedded Systems in Space. Let's give a big hand, a round for applause please for Przemysław Szecówka.
So just let me repeat again that I am FPGA developer in Rockwell Automation. I am also lecturer in Wroclaw School of Information Technology, local small private held university. And I know you might find it annoying when someone refers to his previous employment, but I need to mention Thorium Space. This is the place where I have learned most of the things I share today. So it is just fundamental honesty requires me to say that. Now, concerning the contents of the speech, it is a little bit difficult to find a good balance between describing difficult environment of orbits and humans' reaction to it, what the engineers do to deal with that, but I tried my best. Concerning space vehicles, I will focus on satellites, mainly because this is majority of things in space, and secondarily that this is the area where I can have something to say. So let's go. First of all, the satellites over our heads are levitating thanks to centrifugal force, which is balancing the gravity. So when we look at this formula, we have gravity on the left and centrifugal force on the right, where big G is gravity constant, big M is Earth mass, small m is the mass of the satellite, R is radius, which is radius of Earth plus altitude of the satellite. And then on the other side we have V, which is linear velocity, and this equation balanced provides the levitation of the satellite, which can last roughly forever because there is no drag, there is vacuum. So the satellite, which is once given the kinetic energy, say launched from the rocket, can stay there forever, or maybe till the next page. This equation can be reduced to the constant relation between velocity and radius. And for instance, for the hypothetical satellite who is cruising at altitude 0, so it is flying just over Atlantic waves, touching their crests, this balanced velocity is 8 kilometers per hour. You might know it from school. And when the altitude goes higher, the speed goes lower. So this is the astrophysics level, easy. Let's go to the next page. The real truth is that there is also some dynamic connection. When the velocity decreases, the balance would be on higher orbit, but it is not working like that. When the velocity decreases, then gravity wins in that equation, so the satellite is pulled lower. But then some energy is converted to kinetic energy, so he is gaining higher speed. And eventually the satellite gains the new balance, which is at lower altitude and higher speed. Now, one more thing. Ideal vacuum, the perfect vacuum, does not exist, especially in our perimeter. So when the satellite is flying on the low orbit, it is emitting some very, very thin matter. And when we have contact of extreme speed with very thin matter, there is some drag. And this drag is substantial enough to make the satellite, which is left alone, traveling just like a brick around the Earth, So it is falling some 100 kilometers per year down. And that holds somewhere between 6, maybe 800 kilometers down to 200 kilometers. So for instance, if a satellite is launched at the 600 kilometer altitude, it should last there for 4 years. If it is 400 kilometers, the expected lifetime is 2 years. You can refer to 2 Wrocław satellites, probably the first one from Wrocław, Kraksat and Światowit. And now the 200 kilometer level is a kind of zero here, because at that level, the matter becomes so much dense that this drag is so huge that the satellite decelerates very quickly. So it decelerates, it goes down. When it goes down, the matter is yet more dense. So from the level of 200 kilometers, it is expected that the satellite will fall down in a few days, which means that it goes down to, say, 100 kilometers, and at the level of 80 kilometers, the very thin atmosphere is aggressive enough that it starts burning. And eventually, it burns and does not fall down to the earth. By the way, this is good information that lots of junk is flying over our heads, but we are pretty safe here because they cannot touch the ground because they are meeting atmosphere on their way down. Well, one more thing. I've been referring to circular orbits. In fact, in the space, orbits are ellipses, and the objects are flying around according to Kepler's law. But we love to reduce ellipses to circles, mainly because if you have circular orbit, then you have predictable altitude. So you don't have to worry that your satellite goes higher and lower, so it is easier to avoid and predict collisions. And this is why humanity mostly loves circular orbits. Well, on the other hand, that simple formula applied to circular orbit somewhat holds to Kepler orbits locally and roughly in such manner that when the satellite on cruising around the ellipse is closer, then the velocity goes higher, just like in that circular equation. And when the satellite goes far, far away, the velocity decreases. There is more, but I shall admit I'm too scared to go there, and I have an impression that you don't want either. Let's focus on 2 troublesome things in the orbit. First thing is temperature. The temperature range may be extreme. For the darkness, where there is no shard, it's total darkness, the temperature can go down to total 0, say maybe 3 kelvins. Whilst in the sunshine, the temperatures can reach 200 centigrades. Some people say even 300 centigrades. This is extreme. And at the first glance, it makes absolutely impossible to any electronics to survive over there. However, we shall remember one thing, that temperature in vacuum has somewhat virtual nature. The temperature means prospective possibility to exchange of thermal energy. How to exchange the thermal energy with nothing, if there is no contact, no matter. So in fact, this exchange is limited to radiation, which is very weak effect in comparison with typical one object touching the other. So at the end of the day, it is not so bad in the real world space, that the temperatures are not so bad. And in fact, the electronics which has military grade or even industrial grade can survive there for some time. Not for long, but for some time. It's not that bad. The bigger problem is radiation. First of all, Earth is covered with strong magnetic field. And this is very good for us because this magnetic field is a kind of shield and trap for space radiation. If this magnetic field was removed, then we would die very quickly. Not so good perspective. And this field is also very nice for satellites because there are so-called Van Allen belts, and these are the places where these particles are especially efficiently trapped, and they stay there for some time, they don't go lower. So fortunately for us, and fortunately for satellites cruising in lower orbits, there is Van Allen shield over our heads, and the radiation is not so bad. So we have 2 spaces where this magnetic field is very strong, and eventually also the radiation is very strong because there are lots of particles trapped. And there is internal Van Allen belt and external Van Allen belt. So internal one appears between 1,000 and 6,000 kilometers over Earth, and you can meet 100 mega electron volt protons there, or half mega electron volt electrons. And there is external belt, where the range of altitude is between 19,000 and 64,000 kilometers. And this one holds mainly 10 megavolt electron-volt electrons, but of course also some other particles of space radiation. There are also other unstable belts which appear and disappear, and there is a little problem that both these belts and these unstable belts are somewhat diving to Earth at magnetic poles. So these are the places where there are sometimes problems with electronics and other devices. But on the other hand, people living in the north can sometimes admire beautiful effects in the sky. Borealis, or sorry, I don't remember that English word well. Okay, so concerning radiation, there are problems and parameters concerning electronics. First of all, the ionizing radiation, of course, it can temporarily cause a malfunction, or it can cause total damage, which is irreversible. So there are some models concerning radiation, and the basic parameter is TID, the total ionizing dose, which is characterization of some circuits which are certified for space, and this TID could be 100 kilorads or 200 kilorads, 300 kilorads. The more kilorads are in the table, the better chip you have. And of course, there are models of single event upsets, single event latch ups, and more single event something things. Those ones are more statistical. Okay, so let's have a look quickly about what kind of orbits we have concerning the altitude, because this is the critical factor for electronics. First of all, we have low Earth orbits. And for these guys, the altitude is between 200 and 2,000 kilometers. The linear velocity is between 7.8 and 6.9 kilometers per second. And circulation period is roughly between 1.5 an hour up to 2 hours. So these orbits are the most friendly, both for humans and for apparatus, because there is magnetic cover, and these satellites make some use of these Van Allen belts because they protect them. And there is also lower cost of transportation, so this is why we love these orbits. And examples are, of course, vast majority of satellites is over there, but spectacular examples are Sputnik, the first satellite which was launched to the altitude of 215 kilometers, which means it survives just for a couple of weeks to make some Americans nervous. Then we have Hubble telescope, which is at 540 kilometers, and we have fabulous International Space Station, which is at the altitude of 400 kilometers. Probably you can guess that these guys lasted there for really long, so they must have some engines which make them staying there longer. So they are losing the altitude, but they are regaining it by getting some acceleration. And the fabulous Starlink swarm is at the altitude of 530 kilometers, although I have some doubts about it because there were some disputes about it and there were some negotiations. Facing these numbers, I would say it was all about the Hubble telescope. They wanted to put this Starlink swarm as high as possible, so they would stay there as long as possible, but below the Hubble telescope, just to assure that there is no danger of collision. These Starlink guys have their own engines, so they can maneuver, so they can alone omit collision with something as big and precious like International Space Station, but it is always, Hubble telescope in this case. But it is always good to avoid some collisions with basic physics involved. Okay. There are also medium Earth orbits which are going higher, between 2,000 and 35,000 kilometers. And the most spectacular creatures that can be found there are the navigation satellites. Both GPS and GLONASS are placed over there. which means that they are working just on the edge of the the external Van Allen belt, which means that sometimes their life can be a bit more difficult. However, this is on the edge, and probably this is how they optimized their position. And eventually we have geostationary orbit, which are very specific. The altitude is exactly 35,686 kilometers. Why this is so important? The linear velocity is some 3 kilometers per second, which makes the circular period equal to 24 hours. So these are the specific orbits where the satellite can make the levitation effect over Earth, and this is static levitation. It is just hanging over some point of the Earth, and it is staying there forever. Of course, these points can be only at the equator, so it is impossible to have something like that in Wrocław. Yeah? Only equator provides this feature. And this is somewhat vintage concept of Arthur C. Clarke, the fabulous science fiction author. In fact, it was his idea that, hey, wait a second, if we put just 3 satellites on geostationary orbits, then they can communicate each other, they can cover the whole Earth, so then we solve all the communication problems. So this is how it started, and then it was moved to satellite TV. And the geostationary orbits are also borderline to the high Earth orbits, which are not so interesting because they are far, far away, and they are only for some weird scientific experiments. Some people say geostationary orbit is also the borderline of so-called deep space. But here, the border of deep space is somewhat fuzzy. Some people say it is 100,000 kilometers over Earth, indeed. Okay. So that was about the orbits. Now let's come to some revolution in space. The classic space approach was building vehicles which were big, bulky, expensive. They were unique and they were singular because construction time was so long that when they finished one satellite and trying to build the next one, the technology has changed in the meantime. So each satellite was in fact different. They were expecting very long life cycle because they are very expensive, and because of that they had to be exhaustively tested and certified. So these tests, these development times, these using the best materials available made the costs yet more higher. And there was kind of accelerating spiral of costs, higher, higher, higher. Everything that time was extremely expensive, and it has been like this since the 70s through the, say, first decade of 21st century. And then the space revolution came. Sometimes they call it Space 2.0 or the new space, whatever. The iconic invention is CubeSat. CubeSat is the idea of the satellite which has dimension of 10 by 10 by 10 centimeters, just a brick like this. In fact, contemporary CubeSats do not necessarily follow this dimension, but this is just the idea. So the main features are, they are small and cheap. They have lower reliability, no problem. They have shorter life cycle. They are very good for swarm replications because they are cheap. So they are handy for massive production. And all that makes them yet more cheap, and all that made the new philosophy of space exploration. Let me refer here to the CEO of one of Wrocław space firms, what he said in an interview to the journalist. The journalist asked him, well, sir, but what happens if your satellite does not work? And his response was, well, then we will launch another one. Thank you. In all that concepts, there are 2 levels of requirements, and this is the crucial distinguishing between the obligatory requirements, which are forced by the rocket or launcher operator, and these requirements are mainly for mechanical issues like vibrations and reactions to vacuum, and of course compatibility with deployer, which will throw away this satellite from the rocket. These things are necessary because it is protection of the rocket and of the other passengers of the rocket. This is just to secure that small, shitty satellite will not break anything around where there are more serious vehicles taken to the orbit. And especially it does not disturb the flight of the rocket, because then some people can die on the Earth. So these are the basic requirements. And there are also another requirements which are somewhat decision of the operator. It is his own decision how he balances the risk and the cost. He is to accept the higher risk, higher cost, whatever. So the dilemmas are solved individually, and there is lots of satellites which were put to the orbit and they didn't work. But no problem, they are cheap. Well, the next were better. But all of them had to be designed well enough and certified well enough to not to harm anything on the rocket. So let's have a quick look of the subsystems of a small satellite. There are some canonic subsystems. First of all, there must be some power source. There is a battery and there are photovoltaic cells. And there is a kind of triangular connection, just like in the car, that we have the load, the electronics, which needs power. We have solar, and we have battery. And in this triangle, there is switching of voltages and currents. There is also onboard computer, which is generic machine which takes care about satellite. Sometimes it controls the power board, or sometimes the power board has its own processor, or sometimes the power board is integrated with onboard computer. But anyway, onboard computer can turn on and off other boards, and also can make the basic decisions what we do right now. We can imagine it as a big finite state machine. And then we have ADCS, Attitude Determination and Control System. The special board and set of sensors and actuators which provide nice maneuvers of this fancy low-cost satellite. The basic approach for these maneuvers is again magnetic field of Earth. It is possible to use just magnet torquers, just coils with cores, or sometimes pieces of wire which are just put to the chassis of the satellite, and these pieces of wire, when combined with the current going through them, make magnetic reaction to magnetic field, so the satellite can rotate or move, something like that. Of course, it cannot change its speed, but it can change its position, just the attitude. And there is a radio, which is necessary to communicate with Earth. And then there is some payload, mysterious part of the satellite, which makes it somewhat specific. This is usually the purpose of its flying. Here we have very nice educational example of some Turkish satellite. This one has the dimension of 10 by 10 by 20 centimeters. So this is something like double CubeSat. And where we can see some of these subsystems here. This one is, I don't know what it is. It is somewhat secret payload. Here we have attitude determination and control systems. And if you have a look carefully there, you can see probably some coil with a core. So this guy is to rotate this satellite. Then we have onboard computer with also some fancy radio to issue some beacon. Then we have batteries. Then we have electric power system. Then we have modem, which means some communication. And XRD, I don't know, again, this is mysterious payload. Probably it has something to do with X-ray something. So this is the basic construction, and there are lots of this type of satellites over our heads. By the way, the Starlink guys are not this type. They are more like old-fashioned satellites, quite expensive and heavy. Okay. The core of the topic today is embedded systems in space. So let's start from the basic definition, what the embedded system is. There are some disputes about it, but in my opinion, this is just combination of electronics and software which interacts with that electronics. So in this context, if you want to implement something like that, typically we need a microcontroller, which is purchased from some vendor. And this microcontroller runs the software and has some interface to communicate with electronics. So the first approach is microcontroller, purchased from the vendor. But there are also alternative solutions, and the alternative solution is microcontroller, which is handcrafted in FPGA structure, where FPGA is field programmable gate array, integrated circuit, which is purchased from the factory, and then you can program it and put whatever you want to it. So in particular, you can make processor inside, some buses, some peripherals, and so on. And there is, of course, an option to make the microcontroller, which is full custom. So this is application-specific integrated circuit. You put some core to it, and then you put your peripherals to it, and then you run the mass production. At the first glance, it sounds pretty stupid in the context of space industry, or maybe it has been stupid for the last 20 years. But now, when we have this big fleet of Starlinks flying over our heads, when there are sometimes space subsystems which companies are trying to sell for several other companies, it is becoming more and more reasonable to prepare specific circuits making some space tasks. Whatever technology you take, there are some most beloved cores for the computers. And of course, legendary ARM is in it, the modern RISC-V is in it, and the Leon can be found there. And sometimes even at the 80 mega, there are some processors based on this Arduino known from processors, which are sometimes used for very simple applications. When we think about comparison, whether to take off-the-shelf microcontroller of FPGA, there are several factors to consider. The first factor is that it is quite easy to get microcontroller which is rad-hard certified, which means it is full certified to fly in space. And the prices are really low. $1,000, you may find it crazy, yes, because typically these microprocessors are between $5 and $10. But $1,000, this is typical space ratio. It is 100 more times expensive, but this is still nothing according to the cost of the satellite. So this is the cheapest solution, of course. And they provide extreme reliability, so we love it. And the problem is that concerning the computing power, it is not as powerful as what you can get from FPGA. And of course, there is closed list of peripherals. So if you need some specific interfaces or you need more of them than you have in any processor, then you are forced to use FPGA just like in any other technology or field of application. So on the other hand, FPGAs, first of all, they are extremely expensive. The most fabulous FPGA certified for space, the price was $90,000. That's a lot, and this is typical space factor. Again, price times 100. Or you can use some FPGAs which are not full certified for space, but then you have questionable reliability, so it is a difficult decision. Of course, the advantages are as usual for FPGA. You have flexible peripherals and interfaces. Sometimes you need, say, 100 SPI interfaces, and you can do it in FPGA. You cannot do it in microcontroller. Or there is higher computing power because there is some parallelism in FPGAs, especially in these bigger guys used in Nokia everyday applications. So these guys have uncomparable computing power. And of course, there is some space for smart hardware-software partitioning. So part of the functionality goes to hardware, part goes to software, and you have some freedom to balance it in FPGA. Okay, so some examples of space controllers. First of all, there is Vorago company, which makes quite reasonable microprocessors. And what we have here, first of all, there is ARM Cortex core, and of course the AMBA bus. There are some peripherals. There is memory, which is inside. And there is very specific hard silicon technology, which provides extreme resistivity to radiation. And it has special case. And of course, there is something like triple modular redundancy applied. I will explain it a couple of pages later. When we have a look at this structure here, it looks just like typical microcontroller. So it's quite similar to fabulous Nucleo guys from ST Microelectronics with similar Cortex cores. This guy has old Cortex M0 core, and here we have these RAM guys. There is separate memory for data, separate for code, and of course this is the drawback of the ARM, that this is old-fashioned von Neumann architecture, unfortunately. So there is singular bus which connects it with both program code and the data. Okay, another example, Geissler. Cobham Geissler fabricated somewhat competitive processor where the Leon core is inside. Leon has fancy story. In fact, it was developed for military purposes. So it is somewhat open, everybody can use it, but the crucial feature of Leon was that the engineers in Pentagon uniforms could always sit down and check its design line after line to assure that no strange thing is embedded inside. So this is what they love. And this is somewhat fancy advantage of open architectures. There is another silicon technology which is called RAD-safe, and this is 180 nanometer CMOS. This is impressive. In fact, this is very small size as for this type of devices. So it is very, say, aggressive and modern. Traditionally, these guys were 1 micrometer in the size. Now, what is funny here that we have this Leon guy over there, but of course we have AMBA bus because this is the standard introduced by ARM some 40 years ago, and the versions of AMBA are still cruising around the world, and everybody tries to be compatible with AMBA, both in processors and peripherals, and this way the constructions like Leo or RISC-V are competitive to ARM, that they can be just connected to the same bus and the same set of peripherals. So when we have a look at this, we have typical peripherals again. So there is some bridge from high performance bus to peripheral bus. And then we have UART, guys, timers, I/O ports, I2C and SPI together, and so on and so on. So this is about processors worth consideration in the context of construction of low-cost satellites. Rad-hard technology for reasonable price. Now we switch to FPGA and we have Xilinx. And this page shows the brief history of Xilinx in contribution to space explorations. So Vertex 4 is a very old series of chips, could be some 20 years ago. And Vertex 5, which has radiation hardness marked as hard, which means the higher. And this guy is a legend. It was used in several fabulous vehicles in deep space, some other planet missions and so on. And perhaps majority of satellites in the geospace uses this guy, yes, and they are flying there for some 10 or 20 years. And now we have something absolutely new. Xilinx released this radiation-tolerant Kintex ultra-scale. Kintex is the modern series of Xilinx chips. I mean modern, say, dating back to 15 years. And this is kind of revolution because this guy is really powerful. So first of all, when we have a look, DSP slices, that means something like cores for computation, and we have 2,000 of there. So roughly speaking, if we take into account that good PC computer has, say, 8 cores, so if you divide it by 8 cores, you can imagine that the computing power of this guy is just like 300 of PCs for very simple operations, of course. So due to this parallelism, it can provide very efficient computations. We have also transceivers, special part of technology which is not purely digital. This is mixed signal, and these guys allow for fast serial transmission, in this case 12 gigabits per second. This is not the highest. The highest nowadays are probably 30 gigabits per second, but for space technology it is something enormous. So we have also lots of flip-flops, which mean registers, and system logic cell count is again quite high. So this guy is just a medium-sized Kintex. Well, just 1 hour before, we have in this room the speech of the guys from Nokia saying that they built LTE station in the moon, and they couldn't say what kind of chips are over there. Me, I would bet 1 or 2 flasks of vodka that would be this guy. But I don't know, they don't know either. No, they don't say either. Okay, let's switch to another technology, fabulous microsemi, or microchip right now. To make the long story short, once upon a time there was Actel company which was most beloved by American military because they fabricated old-fashioned FPGAs in old-fashioned technologies, and they were excellent for space, aerospace, and defense application. Then Actel was acquisited by Microsemi, which was then acquisited by Microchip. So what we have right now, first of all, we have RTG4, the legendary rat-hard legend, which dates back to Microsemi or maybe even Actel. And again, this guy was extensively used in several spectacular missions. We have something new. There is Polar Fire series of FPGAs, and RT means radiation tolerant, and this is new technology. But concerning Microsemi, in fact, we can consider all of them. Polar Fire, Iglo 2, Smart Fusion 2, typical FPGAs, which have moderate prices like $100. In fact, we can consider all of them to be reasonable for space because of some specific features. First of all, they are all flash-based, while typical FPGAs are based on SRAM. So the configuration of FPGA, in this case, is in the flash memory, which is inside the chip, and this one is much more immune to radiation than SRAM, which makes it more resistive to single event problems. Another thing, some of them have fabulous column grid array case. The typical chip has ball grid array case, which means that there are some balls on the bottom of it, and these balls are used to solder it to the board. Column grid array means that instead of the balls, there are, say, nice, long, sexy legs. And these legs provide extremely higher reliability concerning vibrations, thermal what? No, thermal stresses, yes. When the integrated circuit expands or shrinks, if this is ball grid array, there is a problem that some of soldering points can click out. Whilst for these nice CGA legs, it is possible to shrink or expand it, say 1 millimeter, no problem. These legs would survive it. So this is something which is clear, visible from the specification. But there are also some rumors in the city. So great source of good rumors is CERN, the guys with accelerators and hadron colliders. Why? Because first of all, they need some electronics which is good for space. And another point is they have possibility to test it. So they test it extensively, and they have also a comfort to exchange it. And there are some surprisingly good results of some experiments in Los Alamos laboratories. And there is something more, but I think I shall not say it here. So let's switch to the next page. There are also on-the-desk hardening techniques. And this is something I need to mention here, triple modular redundancy. It can be applied to various levels. One level is, say, several boards. Another level is you take 3 integrated circuits. But it can be also applied down to the structures of integrated circuit. And the basic idea is you take 3 modules, you take the voter, and this is your output. Wow, this graphics is great. Now, of course, the problem comes, what happens if the voter breaks down? Yeah? So there is solution for that, and the solution is like this, that we have triple modules, 3 voters, again 3 modules, 3 voters. So in such case, if you have breakdown in this part of circuit, in this voter, and maybe in that voter, still the result is reasonable, and this kind of chip can survive a lot here. So this can be found in some synthesizer for FPGAs like fabulous Simplify from the Synopsys. Okay, now about software. Most of this embedded electronics is controlled by the software. Usually it is run on separate processors. And here I need to accelerate a little bit. We have several issues to cover. First of all, there is onboard computer, which is in fact huge finite state machine. And the concept of finite state machine oriented programming is very important over there, together, of course, with some operating systems or their fancy substitutes like building everything on interrupts. There is also issue of telecommand and telemetry processing. And we have separate software for attitude determination and control systems, where some fabulous algorithms like B-dot, triad, vectors, quaternions are performed. B-dot stands for the derivative of magnetic field, and this guy is used for detumbling just to stop the satellite rotation. Triad means conversion of one vector to another, just to detect the attitude of the satellite. And of course, quaternions are very important here. This is fancy extension of complex number concept, which is expanded to three-dimensional space. And Kalman filters for sensor fusion, but we need to speed up a little bit. Another portion of software is radio and antenna, when we have traditional modulation, filters, sometimes beamforming, because satellites sometimes have multi-patch antennas. And we have encapsulation, and we have some redundancy. Reed-Solomon codes, Viterbi codes, these ones were used in, again, ancient satellites and some fabulous missions like Voyager. Recently, the turbo codecs known from some, say, cellular communication are used. And of course, there is question of encryption, just two issues. It is very reasonable to make the encryption for transmission from Earth to the satellite, so nobody captures your satellite. On the other hand, it is somewhat forbidden, not wanted, to make encryption from satellite to the Earth, because the satellite is flying over various countries, and some of these countries may not want to have some encrypted transmission in their territory. Yes, they never know what it is. So here we have competition between traditional ciphers like AAS 256, but also stream ciphers where the Bernstein concepts like salsa, rumba, cha-cha are worth consideration, because for stream ciphers, you don't have to send a block of data to make it encrypted. So it is very practical if you want to say, send just a couple of bytes. And there is, of course, image processing problems and pattern recognition, where the AI methods comes, like maybe Kohonen networks for pattern recognition, or CNN, convolutional neural networks. There are, of course, protocols, and here the software engineers must deal with classic protocols for peripheral communications like SPI, I2C, UART, and there are also higher level protocols which are meant to communicate between the boards. And this is a very old military standard from USA, both military and space. We have new standard, which is space wire. Now, funny thing, the CAN, known from automotive, is extensively used in satellites. And we have very specific CSP, CubeSat space protocol, which was designed for small, fancy satellites. Just don't to pay the royalties for CAN, or don't cope with complicated protocols. I'm coming to the end. A few words about the software reliability. First of all, there are these radiation problems, and if we think about mitigation of them in software, we have this dilemma. We can, first of all, reduce the software, because, in fact, what matters here is the byte count. You have the surface of your chip, you have some space radiations, and probability of hit increases with the area. So you cannot go down with the size of your technology in silicon, because that would be yet worse. So eventually what matters is how many megabytes of code you need to run your satellite. On the other hand, of course, you would like to have handling of some unexpected events, which makes additional branches, handlers, and from this moment the megabyte count is rising, so you have a dilemma to solve. I cannot solve it here, of course. But there are some issues which can be addressed. First of all, technology. The memory chip technology can provide higher or lower reliability. And again, the best guys are probably the MRAM memories, magnetoresistive, which are very good. They are just 1,000 more times expensive than DDR memories, which means 1 megabyte for 1 gigabyte, something like that. But if you don't have too many megabytes, you can afford it. There is also flash memory, which is, again, well known to be more resistive to radiation. And traditional SRAM, DRAM, DDR guys, they are not so good here. But what is worth consider, again, triple modular redundancy and single error correction, double error detection methods. That's all that can help you make your software more reliable. And now another problem which software engineers create are the layers. Of course, we need layers because we are contemporary modern programism, so we have tons of layers over there. What is the weird situation is that sometimes there are problems between one team and another team. And the solution for this problem is to hire a band of mercenaries to make the layer between those two layers, so the problems in the crew are solved because they don't have to communicate. So this is the place for soft skills to be applied to save the world in the space industry. And there is also a question of language, frames, libraries. Let me switch to something which is very in fashion recently. There are lots of talks about so-called green programming. So here I have shown the Winnie the Pooh story of programming languages. So it all has started with assembler a long time ago when the code was given in hex codes or sometimes in mnemonic. Who did it? Wow, lots of you. I'm impressed. Okay. Then there were some languages introduced which provided easier user interface. So there was Fortran, there was Pascal, but the problem was that the compiled code size, or in other words, execution time, increased, which means that from the space point of view, it was worse and worse and worse. More megabytes and more nanoseconds to process the code. But then something strange happened. C was introduced. In fact, it was developed together with Pascal, but it got popularity some 10 years later, maybe because Pascal was created by Niklaus Wirth, who was kind of godfather of programming techniques. And this is something unusual here, just the black swan, that you introduce new language, which is more efficient. Perhaps it never happened again, except maybe Rust is just one more step in this fancy history. Okay, and then we were going farther and farther, and the record word is the Python and Ruby. So when I see someone talking about using Python for space explorations, I am a bit scared. So the phenomenon of 40, maybe 50 years of C language domination is that it is the language which is probably the most efficient and still quite reasonable for the user. Two conclusions. First of all, I have an impression that there is lots of young audience, so I would like to say that space projects are really exciting. But you need to be prepared if you go there that the everyday reality can be a little bit disappointing, especially concerning the certification tests and so on. We don't like it. So be aware that it might be not so interesting. But there is lots of space for you, of course, and I didn't mention several things, maybe ground stations and some data processing issues. There are substantial change of mindset required to go there, so be prepared for that if you want to go there. And I shall say that I observed this new space rush a couple of years ago, and now it is going very well, and I think it will be like this for a couple of years. So you are welcome to join. Thank you very much. Thank you to the audience. And by the way, I would like to thank all those people from the space industry I worked with for the 4 wonderful years in Thorium Space and neighborhood. Thank you.
Let's have a big one. Przemysław Szecówka. Wonderful. If we can just take 1 or 2 minutes of your time, Przemysław, any thoughts, any questions, any insights? Yeah, we've got one over here, please.
So, okay. So you showed this microcontrollers scenario where you buy off-the-shelf microcontroller, right? And
yes.
It has limited peripherals. Wouldn't it be possible just to, like, retro-fashion expose the bus to the pins and just connect some custom peripherals to it in this scenario? So you could have, like, certified or radiation tolerable microcontroller, and then you could expand it using this AHB bus or something like this exposed to the pins of the microcontroller?
Yes, that sounds reasonable. This is one of solutions to avoid high costs. However, you need to remember that every additional circuit means additional connection, additional paths on board, so that brings additional risk. It's better to have just one chip.
Hello, I have a question regarding the communication. Do you know whether the communication from the satellites to the Earth is somehow standardized? Are there standardized protocols, frequencies, or let's say every vendor of the satellite has its own solution? How does it look?
There are two responses. First of all, it is not standardized. You do whatever you want. Yes, so there are several things in use, including fabulous LoRa. But on the other hand, some satellite operators rely on some ground stations. And then these ground stations they have some standards. So it is your choice whether you obey the standards and connect to some ground stations run by another operator, or you build your own ground station, and then you can do whatever you want.
Okay, thank you.
Okay, hello. Another question. How about making everything more bulkier? I know that this will be bigger mass and so on, but we are talking about those radiations and so on. In older days, you know, you just gave bigger voltage, bigger wires, bigger chips, and everything worked a little better. Someone would say that if you electron tubes were indestructible. I know that making a bigger computation on tubes would be insufficient to say, but do you see this trend that everything is smaller, so those problems are worse and worse?
Well, in general, in technology, there is a problem that smaller chips are less reliable. So I shall not say too much, but in the aerospace industry, there were some problems with some very well-known aircrafts where very modern electronics was used, and that electronics was breaking quite frequently. And the same in space. Of course, it's better to stick to the old technologies. So as I said, the micro-semi chips were very popular, the legacy of Actel. But on the other hand, when you want somewhat more higher sophisticated functionality, then you must go to these bigger chips, and to make them bigger, they need to go with the technology down. So the solution is somewhere else. Alternative silicon technology, which allows to big complicated chips with small nanometer size, but still resistive to radiation. Or in other words, talk to the Nokia guys who were presenting it here and go and propose them to take old-fashioned simple microcontroller and build the LTE station on that microcontroller and check their reactions. They don't say anything, but check their reactions. Or
with this
take the Starlink, yes? Enormous machine providing fast internet communication, and again, you need sophisticated circuits for that. So you need to go down with the size of the nanometer structure. So you are right, but we cannot stay in that point.
Okay, thanks.
I would like to ask, you mentioned that buying the radiation-resistant FPGA is quite expensive. I would like to ask whether it's possible to implement the 3-unit redundancy within a single FPGA unit to reduce the costs?
Yes, it is. Maybe I was going too fast, but that's what I have shown, that there are some FPGA technologies where you can just click constraint to make the triple modular redundancy, and the whole chip inside, every piece of it is triple with the voter. So of course you can do, and this is one of the best ways of mitigate the risk using reasonable but not space FPGAs for space.
Thank you so much for your questions. Thank you very much. I think we need to move on. Feel free to grab Przemysław later during the break or hopefully during our after party. Other than that, when it comes to your talk, Przemysław, I think I can reasonably say that we are all over the moon. Pun intended, thank you. And let's thank Przemysław Szecówka.